Hello, today I want to show you a very fast sine-cosine generator algorithm which needs no table. It needs only two shift operation, an addition and subtraction to calculate the next sample point. How it works in detail I will show you after the intro. As I said in the introduction, today I will show you a very efficient sine-cosine generator algorithm. It is idle for small microcontrollers and generates sine and cosine at the same time. It needs no lookup table and no floating point operation. To calculate the next pair of sine-cosine values, only two shift operation and addition and subtraction are necessary. As you can see, the values sine fast and cosine fast, which are calculated with the algorithm, are very close to the values from sine and cosine, which are calculated with the normal function calls. First I will show you the basic idea of the algorithm, and then with the mathematics I will show you the way from the basic idea to the C code. Then I will show you an Arduino program to find the best parameter of the algorithm, and I will do a comparison of the data from the algorithm with the data from the floating point sine-cosine functions. At the end I will close the video with some final remarks. The basic idea is very simple. If you have a vector and let it rotate around a circle, its x value is always the cosine value and its y value is always the sine value. We see here always the cosine value and here the sine value. I rotate now the vector around the circle, and you can see how the sine and cosine values are adapted to the related values. Now some mathematics. To rotate a vector you must multiply the vector with the rotation matrix to get the vector after the rotation. To do this you must multiply the x value with the first column of the matrix and the y value with the second column of the matrix. We will get xr is cosine alpha x minus sine alpha y, yr is sine alpha x plus cosine alpha y. Now we will change in the second line these two terms, move sine alpha x to the end and cosine alpha y to the beginning. Now our rotation calculation has the following form: cosinus alpha multiplied with the vector and sine alpha multiplied with this vector. When we do the calculation with alpha 90 degree, cos alpha becomes 0, so this part will be removed, and sine alpha become 1, so it remains minus y plus x, as you can see here. This means when you want to rotate a vector by 90 degree, you only need to take its y value and use it as the minus x value of the rotated vector, and use the x value of the original value as the y value of the rotated vector. Now we get a better understanding of the rotation calculation. It is the original vector shortened by cosine alpha, which is this part here, and the 90 degree vector shortened by the sine alpha, which is this part here. If we want, for example, to do a rotation with 22.5 degree, we will have about 0.92 of the original vector, which is this one, and about 0.38 of the 90 degree vector, which is this part, and we are again on the circle point. I have done here the calculation for alpha 22.5 degree. Here we have the sine value of alpha, and here's the cosine value of alpha. The sine and cosine values are constants, so we need only one calculation of it. Here we have the starting point of our sine wave generator, and here's the formula. As you can see, we move now with 22.5 degree steps around the circle. Here's the sine and cosine values. I make now the angle a little bit smaller, 15 degree, and we get smaller steps on the circle and the sine wave gets smoother. And with 5 degree we have already a pretty smooth circle and a pretty smooth sine and cosine curve. Now we want to do a further simplification of the formula. With small values of alpha, cosinus alpha is close to 1. We will do a hard step and set cosinus alpha is equal to 1. So we get the rotated vector is the original vector plus sine times the 90 degree rotated vector. With concrete numbers for 22.5 degree we get the original vector plus about 0.38 of the 90 degree vector. So we have here the original vector plus the shortened 90 degree vector, and we land outside of the circle. If we continue this, we will move on a spiral. Here's a calculation for the assumption cosine alpha is 1. So here cosine alpha is removed and we have the original vector plus sine alpha times the 90 degree vector. Here we have the angle alpha, 22.5 degree, the sine value of it, the starting point for x and the starting point for y, and here's the formula for the following points, and here's the formula for the following points y. Now you can see we move on a spiral and the sine and cosine values gets bigger. If I decrease the angle, the spiral gets tighter and the increasing of sine and cosine is not so fast. And now with 5 degree the spiral gets even tighter. But we are not moving on a circle, so we need further improvements. Now the trick how to come back to a point on the circle. First we calculate the x value. It is the original value, it's here, minus the shortened 90 degree vector, and our new x value is here. If we use instead of x, xr, here we have x, xr, x, xr, the 90 degree vector will move a little bit counterclockwise, and it turns out our target point is back on the circle. Here our new formula where we calculate the y value with the already calculated x value. Our alpha is 22.5 degree, here our sine alpha. Here's a starting value for x is 1 and for y is 0. And here's the formula for the following up points for x. And here's the formula for the following up points for y. We have now here an ellipse instead of a circle. This means that the phase shift between sine and cosine is not 90 degree. This is a disadvantage of this algorithm. But this disadvantage becomes smaller if the step width is smaller. If I go to 15 degree, you see it becomes a little bit more cyclic. And if I go to 5 degree, it's already close to a circle, and with 1 degree it looks like a circle. And you see also on the sine and cosine values that the phase shift is now again 90 degree. For the next simplification we can see that sine alpha is a constant factor. So we can write xr is x minus factor y, and yr is y plus factor xr. And factor is calculated roughly with 2 pi divided by steps per circle. Here our formula with vector. Our initial vector with the related angle of 22.5 degree, the initial value of x, the initial value of y, the follow-up formula of x, the follow-up formula of y. Here we have our ellipse. Now I change the factor to 0.3 to 1 divided by 4 to 1 divided by 8 to 1 divided by 16. And we see we have already a good circle, and the sine wave and the cosine wave looks very pretty, and the phase shift is nearly 90 degrees. Due to the fact that we need not to store the old sampling points, we can do further simplification. After the first line is calculated, we do not any longer need the variable x. So we can replace xr here and here by the variable x. After the second line is calculated, we do not need any longer the variable y, so we can replace yr by y. And if we now replace x by the name cosine and y by the name sine, we have the program code for the sine-cosine wave generator. And in the last step we can optimize the algorithm through a favorable choice of vector. Vector 25 means shift the value 2 bits to the right. Vector 0.125 means shift the value 3 bits to the right, and so on for other values. The final code in C is cosine is cosine minus sine shifted 2 bits to the right. Sine is sine plus cosine 2 bits shifted to the right. For other vectors the code looks equal but with different shift values. Now we want to look how the code operates on a real microcontroller. I use the Adruino Nano board, but it should work on each microcontroller. I have written a small program to analyze the sine wave generator. I will put it in the video description below. Unfortunately, the video description did not accept the lower and higher sines. So if you copy the program code from the video description, you have to adjust these two lines, lower and higher sines. Then in these 4 lines, the lower and higher sines. And in these 2 lines, the shift operation. At the Arduino IDE, you can select a monitor or a plotter as an output device. Select here the constant monitor accordingly. True is for monitor and false is for plotter. If monitor is selected, the actual step counter, the minimum and maximum value of sine and cosine, and the actual value of sine and cosine is sent to the output device. If plotter is selected, then these 2 fixed lines are output to the plotter to avoid rescaling of the plotter, and of course the sine and cosine values. With the constant adjust 0 255, you can select whether the output values should be in the range from 0 to 255 or in the range of minus 128 to plus 127. Init cosine is the initial value of cosine, which is roughly the amplitude of the sine wave generator. Shift determines how many bits the values should be shifted to the right, and with offset you can move the complete curve up and down. Here are some good values for init cosine and shift. Good values are values where the sine wave generator returns exactly to the starting point after 1 cycle. More details on this later. With the offset you can align the output to the top, centered or to the bottom. And here's the related information of the output: the steps per cycle, the range of the sine wave, and the range of a cosine wave. In the setup routine, you must ensure that the selected bitrate fits to the bitrate you have selected in your plotter or monitor. The subroutine print values sends the data with the above selected configuration to the monitor or plotter. Now to the sine wave generator. We have two 8-bit signed variables. One is called sine and is initialized with 0, and the other is cosine and initialized with init cosine. The two print lines should give some space after the previous output cycle on the monitor. Here we have the main loop. First we print out sine and cosine and then calculate for the next step cosine and sine. And the loop will run until we are exactly on the starting point, when cosine is equal to init cosine and sine is equal 0. Finally, we print the last values of sine and cosine and run in an endless loop to stop the program. This sine wave generator runs until it returns exactly on the starting point, no matter whether it is one cycle or infinite cycles. We will now have a look on some values. We start with init cosine 124 and shift 3 and offset -3. We start the program and we see we have exactly one sine wave cycle. Now we change the init cosine value to 121 and start the generator again. And now we have a lot of cycles and a change in the amplitude, which is like amplitude modulation, and this is what we not want in our cosine sine wave generator. I will now remove the stop condition to get an endless loop. So I insert here an infinite loop condition and a delay, so that it runs a little bit slowlier. I started now again the code. And we see here this amplitude modulation. It goes up and down. And when I now change to a value where we have only a single loop, then we see we have a constant amplitude. Here very constant amplitude on both sides. And I can now change to some other values here from the table. I make it init cosine 126, shift 4 and offset -7 and start again. And we see the sine wave is now a little bit slowlier because we have more steps for a cycle, but the amplitude is exactly the same. At this table I have summarized some good values for init cosine and shift, which means after one cycle the generator goes back to the initial values, with the consequent with infinite loops you have a constant amplitude. Now I want to compare the output of the sine wave generator, here called sine fast and cos fast, with the output of the floating point sine function and cosine function when it is rounded to an 8-bit integer. With an init cosine of 120 and a shift of 2, we get 25 steps per cycle and a cosine phase shift error of minus 7.3 degree. And we see that the sine function is really very close to the original sine function. Only the backdraw is the phase shift error here to the cosine function. With an init cosine of 124 and a shift of 3, we get 50 steps per cycle and a cos phase error of minus 3.7 degree. And also here the output of the generator is very close to the original sine function, and the phase error is now a little bit smaller. With an init cosine of 126 and a shift of 4, we get 102 steps per cycle. The cosine phase error is now minus 1.8 degree, and the generated sine wave is still very close to the original sine wave function, and the phase error was decreased further. With init cosine 126 and shift 5, we get 212 steps per cycle. The cosine phase error is now decreased to minus 1.1 degree. But now, even with this high sample rate, we have here straight lines, and the reason for that is this shift factor of 5. Shift of 5 means divided by 32, so values below 64 will result in 1 point something, which is then rounded to 1.0, and therefore we have here a constant increasing with 1. And values below 32 will result in 0 point something, which will be rounded to 0, and therefore we have here a flat line. Then again 1, 2 and so on. So a too high shift factor will increase the number of sample points but decrease the approximation to the real sine wave. As we have seen, this very simple 8-bit sine cosine wave generator delivers very good results even with its simplicity. The only backdraw is the phase error between sine and cosine function. And we need to take care of the shift factor. We can use 2, 3 and maybe 4. With 5 we get the visible degradation of the approximation to the sine function. That's all for today. If you like my video, give me a thumbs up and subscribe my channel. And to be informed about new videos, activate the bell. See you in the next video. Bye bye.